Lesson 12.5, area under a curve and integration. We get into some fun mathematics today, but before we do so, let's go over a derivative again. If you remember, we last class learned about derivatives and how excellent of a shortcut derivatives can be for determining limits. So that's what we're going to look at here first. Let's take a look at number one. Find the derivative of the function f of n equals 2n cubed minus 4n squared plus 7n minus 1. So let's go over this. If you remember the rule for derivatives, when you find a derivative, the way you symbolize it is we write f prime. That's what they call that little apostrophe there. F prime of n, that means the derivative of f with regard to n. You take the powers, you multiply the coefficient in the front. So 2 times 3 would be 6. And then the powers you subtract by 1. So 3 minus 1 is 2. Now whenever you're doing derivatives and you have a polynomial, you'll treat each term the same way. So now I go -4 times this power of 2, which would be a -8, n, and the power 2 minus 1 equals 1. So it'd be the power of the first, which I don't need to write the 1 there. Next term here, this is like a power of 1. So 7 times 1 is 7. 1 minus 1 is 0, so you don't have to write n to the 0th power. That will just disappear. And a constant always, when you take the derivative, disappears. The derivative of constant is 0. So this would be my equation here. And so when it looking through our answer choices here, looks like the answer would be A. All right, and let's look at number 2 here. It says find the derivative of the function, and this time cranked up the difficulty a little bit by using fractions. So if we wanted to find the derivative of b with respect to f here, let's see, b prime, what you would do is you take your power 4/3 and you multiply the coefficient 3 by 4/3. This is like saying multiply by 4, divide by 3. But that's how fractions work. So I'm multiplying 3 times 4, but then dividing by 3. So ultimately the 3's will cancel out. We'll be left with 4f. Now it'll be 4/3 minus 1, which 1 is the same thing if you get a common denominator as 3 divided by 3. So 4/3 minus 1/3, or 3/3, is 1/3. So it'll be 4f to the 1/3 power. And over here, I have a -6 times 3, which would be -18. Divide that by 2, I get a -9 f. And now we have 3/2 minus 1, which again, 1 you could rewrite with common denominator as 2 divided by 2 to the power of 1/2. And so our solution from here, it looks like a C. Let me make sure that that's 7/3, that's a 12, 7/3, 9/4. Yeah, that would be out. So it would be C there. Just to remind you though, I do want to show you that you could rewrite this function here. The power of 1/3 is the same thing as the third root of f, and f in the inside of the root would have the power of 1. That's where the 1 would go, would be the inside. The division power, dividing of 3, is a root. So it'd be 4 times the third root of f minus 9 times the square root of f. A square root is like dividing by the power of 2. So you could write it this either way here. Those would be the same answer. All right, so today we get to look at something pretty cool. It's finding the area under a curve, which we call integration. And so what we're going to look at is we have these different words. You're going to see, and you're going to hear me say Riemann Sum. I'm going to draw your attention to that word here. This is a pretty neat little deal. So first off, it says approximate the area under the curve of f of x here and the x-axis. So between this curve and the x-axis, we're trying to find out how much area is under this curve. And we're going to do so using what we call this rectangular techniques. It's kind of a Riemann sum is basically what we would call it. And now it says find the right endpoint of each rectangle to determine the height. So let me show you over here what we're doing. I'm going to type in that function of f of x. It said f of x equals -x² in the problem plus 18x. And I'm going to zoom out just a little bit. So there's the picture. And what we're trying to do is find the area that's, let me see if it'll do it, if it'll shade this way. No, it won't. Okay, so we want to find the area that is underneath this curve, but greater than the x-axis. Oh, I know how to do this. Make it a y. If I make it a y, now I can say it's less than or equal to. So I want to find the area under here, but it's also has to be greater than the x-axis, where y is greater than or equal to 0. So we're looking at this area of the curve. That's ultimately what I'm trying to find, is this shaded region. And so there's different techniques that mathematicians use to try to come up with that area. And so one of them is by using these rectangles. And so what they're going to do is it says using 6 rectangles. If you count out, there's 1, 2, 3, 4, 5, and right here would be the 6th. So I have 6 rectangles of equal distance apart. So since this goes from 0 to 18, the total distance here is 18 units. From here to here is 18 units. And since I want 6 rectangles, they just take the 18 divided by 6, and we get rectangles of 3 in width. Should say 18 units divided by 6 is 3 units. So that's why each of these rectangles is 3 in width. And so when I try to find area, remember for a rectangle, it's the length times the width, or base times height, if you will. And so the base on each of these rectangles is going to be a length of 3. So all these rectangles is going to be a length of 3. The height is going to be determined from the function here. This height of this first rectangle is going to go up to this point, the point of f of x at 3. So now what I'm going to do is I'm going to come over here and I'm going to copy what we had originally. I'm not going to graph it though, and I'm going to change it back to f of x, and I'm going to use the table to help me out here. So I'm going to hit and go to table, and I want to make this count by 3. So we want the rectangle that goes from 0 to 3, and we're using what's called the right endpoint, meaning the height is determined by what the height of the function is on the right side, not the left. That would be a rectangle here at this point. But we want to know what's the height on, if you made each rectangle, the height of where the right endpoint would be. So at 6, this next rectangle, the reason it's way up here is because at 6, which is the right endpoint of this would be left side, right side. The right side of the function is way up here. So that's how they created this rectangle. So what I'm going to do is I'm going to count here by 3. So 3, 6, 9, 12, 15, and 18. So I see those are the heights of those different rectangles. And so now, how would I do my math? Well, we know each time, so remember the area of a rectangle would equal the base times the height. So for the first rectangle, we will have an area that would be 3 times the height of f of 3. So what I'm doing is the width here, or the base, times the height, which f of 3 is 45. So when x is 3, we have a 45. So it's 3 times 45. And now I'm going to show you a little trick here. So the calculator will do the math for us. What I'm going to do here is I'm going to say 3 times f of x. And so you'll get to see the math. I don't even have to work out the math. It'll be written out right here, which will be 135. I just typed in 3 times f of x. So it just triples all these values. So now the next rectangle, that's the first rectangle. That's the first rectangle. Now here's the second rectangle. So we're now looking at this rectangle. So this rectangle right here is 135 units squared. 135 units squared. Okay. I guess I could put that here too, units squared. Okay, so the next one would be 3 times f of 6. Now why f of 6? Because that's where the x value is 6 at the right side of the second rectangle. So 3 times 6 would be 3 times 72. That's the height that's at this point is 72, which is going to equal 216. And so we'll go on all the way down. Now I'm going to start kind of speeding this up a little bit. 3 times f of 9, which 3 times f of 9 is going to be 3 times 81, or 243. Okay, And we'll continue on here. So the fourth, 3 times f of 12 will equal 3 times 72, which is 216 units. Oops, units squared. There we go. And we got 2 more here, 5 and 6. So the fifth will be 3 times f of 15. So 3 times 45, which is 135 units squared. And then finally, 3 times f of 18 is the last one. It was just 3 times 0, which I don't need the calculator for that one. This would be 0 units squared. So if I wanted to approximate the area under this curve using these rectangles, I could say, all right, let's just add it up. And the total would be our approximation of the area under the curve. Approximate area under curve would equal the sum of these numbers, which let's just type these in real quick to make sure we don't make a silly mistake. 135 plus 216 plus 243 plus 216 plus 135, and if for good measure you can do plus 0, but that won't change it. The answer is 945 units squared. 945 units squared. Now you might be looking at it going, okay, so that is our approximation, but how accurate is it? I'm looking and there's a lot of white space over here, but there's extra over there. Now, is that accurate or not? I don't know. How could we figure it out? Well, part B says, here's one thing we could try. What if we made our rectangles smaller? So instead of having a width of 3, what if we made them have a width of 2? So notice our rectangles here have a width of 2. And so now I'm using the same problem, but with 9 rectangles. So this time, what I'm going to do is I'm not going to count by 3s, I'm going to count by 2s. So we'll have 2, 4, 6, 8, 10, 12, 14, 16, and finally 18. Notice that'll be 9 rectangles. 1, 2, 3, 4, 5, 6, 7, 8, 9. That's 9 rectangles. And this time, since my width is 2, I don't need to multiply these values by 3. I need to multiply these values by 2. And this will give us our correct value. So this time around, I'm just going to double all those values. So we could write these out, but to be a little bit quicker this time, I'm not going to write out all the math. I'm just going to say, okay, 2 times f of 2. This would be the area for this rectangle. 2 times f of 2 is 64. And this would be units squared. 2 times f of 4 is 112 units squared. 2 times f of 6 will be 144 units squared. 2 times f of 8 would be 160 units squared. I think you get the pattern. 2 times f of 10 is 160 units squared. I'll write that later. 2 times f of 12, so we can see that we're now getting symmetrical here, is 144. 2 times f of 14 ought to be 112. Let's check. 112. Yep. 112. And then finally 2 times f of 16 should equal 64, which I say I'm done there only because 2 times f of 18 is going to equal 0. And so we would need to add all these up to get our total area under the curve. So if I add these values up, we have 64 plus 112 plus 144 plus 160 and another 160 and another 144, 112, oops, 112, and finally a 64. And we notice that this area is actually 960 units squared. This is 960 units squared. So we see that we were undervaluing the area. I'm going to guess that on the previous problem, we were actually undervaluing the area because it looks like to me that this using 9 rectangles is more accurate. And so one more time, I want to look at this, but this time let's get even more accurate. If it appeared to be more accurate going from rectangles with a width of 3 to 2, what if we had rectangles that had a width of which 1? Would this even be more accurate? And so we're going to use the same problem, but now use 18 rectangles, which meaning the rectangles have a length of 1. So it's just going to be 1 times each of the values. So I'll have 1 times f of 1, oops, 1 times f of 2. You get the picture. It'll be 1 times f of 3, and so on and so forth, until we get to 1 times f of 18. And so now I'm going to come over here. These values are going to get multiplied by 1 this time, and we're going to look at the values from 1 to 18. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18. Now I'm going to add up these values. So I'm not going to show the algebra this time. I've shown it twice now. I'll just add these up. So we have 17 plus 32 plus 45 plus 56 plus 65 plus 72 plus 77 plus 80 plus 81 plus 80. And now we're going to go down that symmetrical. So we have 77 plus 72 plus 65, whoops, plus 56 plus 45 plus 32 plus 17 plus 0. Now, I'm not saying I didn't make any mistakes, but it appears to me that this area is 969. So this time we'd have 969 units squared for our area. And just one more time, just to be clear, what we are saying is like this box right there is 17 units squared. 17 units squared. That would be the first box. The second box would be 32 units squared. Just going to use UN. The next one will be 45 units squared, and so on and so forth. So you could just that each one of those boxes, and you can see that this appears to me to be a lot more accurate because you have less white space than, say, the first equation. We have less white space, and we have less shaded outside the curve. It just each time it seems to be getting minimized. And so that's a better way of representing. So that's what we call, a lot of times we'll call that a Riemann sum. Finding area under a curve is adding that up. As you can see, that was a process and it was quite lengthy. So I'm going to simplify yours, and I want you to use this equation and find the area using rectangles, like 2 rectangles and 5 rectangles, meaning if you use 2 rectangles, they're going to be 5 apart. So you'll have one that's a length up to 5, and the other length goes from 5 to 10. And then using 5 rectangles, which means every 2 units. Okay, so use those to come up with your numbers and see how accurate they are or how much they differ. Example 2, area under curve using both left and right endpoints. Okay, so on example 1, we only looked at the right endpoint. So making these Riemann sums is what we're going to learn. It's called these blocks going from the right endpoint. And we add those up for the area. So this time my function has changed. So I'm going to come over here and change my function. And we're going to look at x squared plus 1. And I'm only going to look from 0 to 4. So let me change this part here, 0 to 4. So Desmos is now showing me exactly kind of what we're looking at. It's this area. And first it says use the right endpoints, which means we want to make little squares kind of going from the right of each unit. Here, let me zoom in. So maybe there we go. Well, I was trying to get the x-axis a little bit better, but where we'd have blocks of length or width 1 unit going from the right endpoint. And so I actually have that up here where you can see exactly what's happening. And so basically we're adding up these areas. So how would we go about doing that? Well, just like number 1, the area of a box is always, or a rectangle, is length times width. So we want the width to be 1 on all of these, and we're using the right endpoints. And so basically what I'm doing is taking the width of 1, so or the base, and I'm going to multiply it times the height. And the height is determined by taking the f. Now, if I want the right endpoint for this block, my right endpoints are going to be 1, 2, 3, and 4. So 1 times f of 1, and then again a base width of 1 times the height of f of 2, 1 times f of 3, and 1 times f of 4. Those are the values I'm going to add together, or sum together to get the exact area here. So if I go over my calculator, I can find out that this first width would be 1 times the height of f of 1, which f of 1 is 2. So as you can see over here, 1 times 2 is 2. Oops, wrote in the wrong place. There you go, 2. The next one would be 1 times the 5 here, which is 5. And then we'd have a 10 and a 17. And if you added that up, you'd get the area in units squared. 2 plus 5 is 7, plus 10 is 17, plus another 17 is 34. So this is 34 units squared. And by the way, if you remember from chapter 10, we learned about how to find the sum using the symbols, the sigma. And so the way you would work this is we were going from the right endpoints where the numbers 1 to 4, from 1 to 4. And each time, what were we doing? We were multiplying 1 times f of whatever the n value is. And notice it gives us 34. Okay, so we did that one correctly. Now let's look at, and this is an overestimate on the area. Notice these blocks are larger than the actual area under the curve would be. Now let's take a look if we were looking at the left endpoints. So this time, instead of saying I want this area, which we got to be 2, this area, which was 5, 10, and 17. If you didn't catch that, that's what these blocks are. That's the area. So like this block has an area of 2 units squared. This one is 5 units squared. This one's 10 units squared. And this was 17 units squared. Now let's look at it using left endpoints. So left endpoints would look a little bit different. Let me turn these off. There's no quick way of doing that other than clicking them all. And now let's look at the left endpoint. So now we're finding the area using left endpoints. Notice this is going to be an underestimate of the area. It's not going to include all the area. And so what would happen is, again, I would do base times height, and we're doing a base width of 1. But this time, using the left endpoints, I would use the values 0, 1, 2, 3. I'm not going to use the 4 because that would be on the right side. I want to use the left side here. So I'm using the numbers from 0 to 3. So it'll be 1 times f of 0, 1 times f of 1, 1 times f of 2, and 1 times f of 3. Now you know why when I program this in, I use the numbers from 0 to 4 because I would need 1 to 4 in the first problem. Now I'm going to use 1 to 3 on part B here. And so the multiplication I already have done right here would be 1, 2, 5, and 10. So the total area, I add this up, 1 plus 2 is 3, plus 5 is 8, plus 10 is 18 units squared. The area here was 1. The area here is 2. The area of this block was 5, and the area of this block is 10. So this was an underestimate. This was an overestimate. Part C mentions that oftentimes people, to try to get more accurate, if they know the left Riemann sum and they know the right end Riemann sum, they might just average these together. Let me type it in the calculator to show you. From 0 to 3, 1 times f of n. Notice we get an 18 this time. Okay, so if we wanted to have a more accurate representation, we could average the two because we know that this one, the part A was too high. We know this one is an overestimate. It's too high. That's an overestimate. It is too high. Because the shaded H block is shaded above the curve. This answer here was an underestimate. It's too low. So more accurate would be to average the two together. If you take that 34 and you add it to 18 and divide by 2, we get the average. This would be the average area. Let's just type this in the calculator. Make sure we don't make a simple error. 34 plus 18 divided by 2 is 26. 26 units squared. Now this would be our a better estimate. Now why does it have to be better? Well, the first one we know for a fact was too high. The second one we knew was too low. So the average between must be more accurate than either of the first two. So it's a better estimate, being somewhere in the middle of those two values. All right. Now, with that background knowledge, let's see if you can work out example 2 DOL. Pause the video. I'm sure you'll need to take a little time to find your answers. All right, example 3, the definite integral. All right, it's time for us to get to what is the exact area. Enough of this estimating and being off. Let's talk about what the exact area is. Well, in mathematics, we call this symbol right here an integral. And what the integral is going to calculate is between the two bounds, or the interval a to b, it'll calculate the area under the curve of f of x, or if f of x were negative, the area between the curve and the x-axis. That's what's always going to happen. It's the area between the curve represented by f of x and the x-axis. Now, I'll talk later about what dx represents. So how mathematically is it calculated? Well, honestly, what happens is this. If you think through what we were just doing earlier, we were looking at the right Riemann sums, which is basically adding these blocks together, and we did the left Riemann sums, and we averaged them out to get a more accurate picture. But that's what we were looking at. We were adding up these different sums. Well, it's going to take the same idea of multiplying the function times the width, where the change of x is the width. Now, we have width of 1 here, and what's going to happen is this limit is going to say, let's make this change of x get smaller and smaller. So instead of us having the bounds subtract by each other, let's divide that, kind of like we did in example 1, by a number that's approaching infinity, which makes the width of these rectangles get smaller and smaller. And so here's a visual to show you what happened. Here's the right Riemann sum. And what's going to happen is I am going to find the area as I shrink this down. And so let me show you visually. I'm going to come over here to my slider. And what I'm going to do is I have created here a list that's going to represent all of these blocks. And what I'm going to do is I'm going to start shrinking the width. Now, as I shrink the width here, you can see that my rectangles start getting closer and closer to the curve. So right now you'd still say that, well, it's an overestimate. There's more blocks outside the curve and every part underneath is covered. So this is an overestimate. Well, as I start getting this be smaller and smaller, you'll start seeing that the overestimate actually starts decreasing. This is not very much of an overestimate anymore. You can see how closely this is coming. And so the idea is this: if we were able to calculate all these rectangles, we'll have a better idea what the area is. That'll be really accurate. Well, what if I keep going further and further? You can start to see this is going to be a really accurate representation. I'll go all the way to there. How similar are these two areas? Well, when you look at them, it doesn't look like much of an overestimate at all. The problem is, how do we calculate this? And I'm not going to get into the algebra today. I'll do the algebra next class of how we can walk through this. What I'm going to show you today is just how to use the calculator to calculate that sum. So how do we calculate the sum here, the sum of all those millions of rectangles? Honestly, I made, let's see here, that's 1,000 rectangles per every unit. There's 4 units. So there's 4,000 rectangles in here. That's what it is right now. Isn't that crazy? 4,000 rectangles. If I wanted to 0.1, if my math is right, that would be 400 rectangles fitting in there. It's extremely small, so small you can't even see them all. So what is that area going to be? Well, what I would do here is I would say int, which gives you the integral symbol, or what you can do also is you can go from your Desmos calculator, hit functions, miscellaneous, and it's right there at the bottom left-hand corner. It's the integral. We're looking from 0 to 4 of the function f of x, which you could type in f of x if you wanted to, like this, dx. And like I said, I'll talk about that dx next class. And this is the exact area, 25.33. But if you don't want to type in f of x, in case you don't have everything typed in, the equation was x squared plus 1. It was just like number 2. Example 3 is the same equation from that we had on example 2. And you see the exact area is 25.3 units squared. 25.3 repeating units squared. Now remember how when we came to example 2c, we estimated that it was 26 units squared, so we were still a little bit over, but this is the exact answer here using the integral. Now, you can just type this part into the calculator and come up with an exact answer. Do not forget the dx. Make sure you type it in just like that, and you should get your answer accordingly. Pause the video if you need more time. All right, example 4. Let's do this integration again, and I'll let you see it now with a different equation. So I'm going to come up here and change my equation. Now, instead of x squared, we'll do x cubed, and I'm going to make that out all the way out to 1. And let me resize this so you can see the picture. All right, here's the right Riemann sum. I don't know if I said that. When you find the definite integral, it uses the right Riemann sum. So there's the right Riemann sum. And I can probably adjust this just a little bit to make it easier to see what's going on. Let's go from -5 to say +6. There we go. There's our right Riemann sum. And we can see this is an overestimate. These boxes would be shaded too wide. Well, if I wanted, and let me make sure I'm looking, we want to find the area between 2 and 4 only. So we're only looking between 2 and 4 on this problem. So I'm going to come over here and change my problem where I'm only looking, I need to go to this A list from 2 to 4. And this B would need to be now, let's make that a 3. That needs to be a 3. And this a 2. Okay, so I might need to correct a few things. Hang on one second. Okay, so I had to just fix a little programming. So we're looking for the area now just between these two values. So we're not just going to search that. I need to unshade that. Hang on one more second. There we go. So we're looking for the area in between here. And so the idea is this. What would be if we shrunk the Riemann sums as small as possible? What would be the area for that part? And what we could do here is just go to our integral, and to be fast, I'm going to just change that to a 3, and we should have the area as being 62 units squared. 62 units squared. Again, what happens there is instead of taking, so like the very first example one, we did right Riemann sums from the right endpoints. Instead of taking the right Riemann sums, which this would be an overestimate, you could do this and find the right Riemann sum. And you would be adding up the values from 2 to 4, which would be 9. Oh, wait, I did it by halves there. So here I would need to do it by halves. If I wanted to do this math right, let me change this to, and I want to go from 2, 2.5, 3, 3.5, and 4. Okay, and so these would be my areas if I was doing the right Riemann sums, starting actually at 2.5. So that would be this area right in here would be like 8.3125. This area right there would be the 14. This area is the 21.9375. Oops, 9375. And finally, this area right in there would be 32.5. And if you added those up, you'd see that that is an overestimate that is greater than the 62. And so that, I'm just trying to show you the difference of what's happening. That would be looking at this Riemann sum. Well, counting by halves. This is counting by ones. But let me go to half, 2.5. There we go. That's the area shown there. On these blocks, it would look like that. But the actual integral, what it does is it shrinks these infinitely small to get a more accurate representation. So with that, you go ahead and try to see if you can find the area for this particular problem here, y equals 2x cubed plus 3, the area under that curve, and the x-axis from the interval 1 to 3. Example 5, business. A clothing manufacturer produces 2,000 pairs of pants per day. The cost of increasing the pairs of pants per day from 2,000 to 5,000 can be found by using that integral. What is the increase in cost? Now, here's one thing that's deceiving is many students will look at this and say, well, the cost decreases. The overall cost will not decrease. The cost per pants will decrease. So this is saying if you make a 2,000 pair pants, this is the cost per one pair of pants. So let me write that on there. This is the cost per one pant, if you will. And so this would be a dollar value all the way across. This is the unit. And these are the pants across here. So that wouldn't have a unit. That's just one pair of pants. Or you could say it's the pant itself. That'd be one pair, or 1,000 pair of pants, 2,000 pair of pants. There's not like a dollar sign with that. And so if you only made 2,000, you'd be saying 2,000 per, or whatever that is, around $13, maybe 12.5. And you multiply it out, and that would be the total cost. What the area is it's going to figure out the total cost, because what it does is it's multiplying these values as I was just doing there. So if this is the cost per one pair of pant, or 1 pant, then it will multiply them, and that's why it looks like an area. It's because it's multiplying the number of pants you make with the cost. And so whatever our answer is, since we're multiplying, it would take the unit $sign. So let's come over here and just figure out what this price would be from if we made 2,000 pairs of pants, and we want to look at the increase going from 2,000 to 5,000 pairs of pants, and the formula is given as 20 minus 0.004x dx. The increase in cost would be $18,000. Does that mean it'll cost $18,000 to make those pants? No, it is not. That's the increase in cost. This right here is the increase in cost. I need to explain this. Increase in total cost. So even though it looks like it's decreasing here, there is an increase in the total cost. Now you might be saying, how is there an increase in the total cost? Well, the cost to make 2,000 pants, cost to make 2,000 pants is 2,000 times, let's just say that's 12.5. I don't even know if that's right. Well, you know what? We can plug it into the formula. 20 minus 0.004x is 2,000. It says 12. That's the cost. That's $12 to make 1 pair of pant there. So 12 times 2,000 pants means it costs to make 2,000 pairs of pants. It'll cost us $24,000. And so when I add, we're going to get here in a second, is 42,000. So what's the cost to make 5,000 pairs of pants? And this is the law of economics here, is typically the more you make of something, the cheaper you get. You get more efficient, you get assembly lines, you buy in bulk, it just gets cheaper. Okay, let's see the cost to make 1 pair of pants here. So I'm going to plug in the equation again, but I'm going to now change. What if it was 5,000? Well, that's saying it doesn't cost anything extra to make another pair of pants. That's kind of ridiculous. But so what I'm going to do here is change it just a little bit. Let's just see, at 4,000 would be $4 per pants. And so, and I might not be getting this math in here right, but yeah, so I'm not calculating this right. This is kind of diminishing to 0, which is not accurate. But overall, this would be the increase in cost would be 18,000, which means the total cost to make 5,000 pants should be $42,000. Now, why I'm not getting it there, I need to go back and kind of look at what I'm doing, but that's beyond the problem anyways. What this is saying is the increase in cost. That's what the cost is to make 2,000, and that would be the increase to make it up to 15,000 would be $18,000. Now here is one for you to try. Pause the video if you need more time. And it should be really simple if you just use your calculator tool to find that integral.